Good morning, my dear students. I hope that by now you must have bought the books because books are required to study physics. Books should be in front of you. But for those who have not bought the books, I have still loaded the book in the video. So you can follow that in the video. Now, in the last video, we had discussed about the first lesson, units and measurement. In this, we had discussed about the unit, fundamental quantities, and fundamental units. We had discussed systems of units, the CGS system, FPS system, MKS system, SI system. Then we had also defined certain fundamental SI units. I had also said that you need not learn the SI definitions of SI units. Definitions are never asked, but you should know them. Okay. Now from today we shall start with derived units. Derived units. So we have very few fundamental units such as length, mass, time, electric current, temperature, amount of substance and luminous intensity. But there are many more physical quantities that are measured in physics besides these fundamental units. So we derive out these physical quantities from these fundamental quantities, and these quantities are known as derived quantities and the units are known as derived units. I will give you a simple example. We have the fundamental quantity of length. Length is a fundamental quantity, and from length we find out area. Area is the square of the length. So its unit will be meter square. Volume. Volume is length, breadth and time. Multiplication of length into breadth into height. Length into breadth into height. And SI unit is meter cube. Then we have density. Density is dependent upon mass and volume. So density equal to mass upon volume. Mass SI unit is kilogram. Volume is meter cube. So SI unit is kilogram per meter cube. Velocity. Velocity is the ratio of displacement to time. So unit displacement meter, time second. So unit of velocity is meter per second. Acceleration. Change in velocity upon time or rate of change of velocity. So its SI unit is meter per second square. Force. Force is mass into acceleration. So SI unit is kilogram. Acceleration is meter per second square. So unit of force is Newton. 1 Newton is equal to 1 kilogram meter per second square. So Newton is a unit that has been named after the physicist Newton, Sir Isaac Newton. Okay. So 1 Newton equal to 1 kilogram meter per second square. Then pressure, force upon area. SI unit Newton per meter square. Another unit Pascal. 1 Pascal equal to 1 Newton per meter square. A bigger unit of pressure is bar. 1 bar equal to 10 raised to power 5 Newton per meter square, which is equal to 10 raised to power 5 pascals. A smaller unit of pressure is torr. 1 torr equal to 1 millimeter of mercury. You must have remembered in barometers the height of the atmospheric pressure. The atmospheric pressure, normal atmospheric pressure at sea level is 76 centimeter of mercury. Okay, so that is equal to 760 millimeter of mercury barometric height. So 1 torr equal to 1 mm of mercury. Another derived unit is work. Work is the product of force and displacement. So unit of work, if we write for force, it's Newton. Newton into meter. And Newton can also be written as kilogram meter square. Okay, kilogram meter per second square into meter. So in MKS system, the unit for work is kilogram meter square per second square. 1 Newton into meter is equal to 1 joule. Another unit named after the physicist Joule. Power. Power is rate of doing work. Work upon time. Work SI unit is joule times second. Joule per second, that is equal to 1 watt. So 1 watt equal to 1 joule per second. So in this way, the unit of any physical quantity can be derived from the fundamental units. These are few examples. There are many more quantities that are studied in physics, and all their units can be derived from the fundamental units or from the units of mass, length and time. Then we have certain guidelines for writing SI unit in symbols. Very important. Otherwise, if you write units in wrong way, you lose mark. So there are certain rules for writing SI units in symbolic form. Small Roman letters are used for symbols of units. Symbols are not followed by full stop. When we write a unit named after a physicist like Newton, so if we are writing the full name of Newton, Newton, then N should start from small letter. That is very important. When you are writing Newton in full form, Newton, then N should be written in small letter. Okay, not capital N. Or we are writing joule, then if we are writing in full Joule, then the unit should start from small letter J, not capital J. Next, if only symbol is written for the units named after the scientist like Joule or Newton, then the initial is always written with capital, like capital N for Newton, capital J for Joule, capital W for W. Is it clear? So when we are writing the units in short form, then only the capital letter should be used. Okay, and if we are writing the units named after the physicist in full form, then the name should begin with a small letter. Then we have the last point. If unit, like we have 10 meter, then unit is never 10 meters. Unit is never written in plural form. Okay, unit it remains singular only. Force cannot be 10 newtons. Length cannot be 10 meters. Unit will always remain singular. It is the magnitude is more than 1, then unit does not become plural. Okay. Then we have prefixes for power at 10. A table is given there. Okay. 10 is 10 raised to power 1 deca, 10 raised to power 2 hecto, 10 raised to power 3 kilo, 10 raised to power 6 mega, 10 raised to power 9 giga, 10 raised to power 12 tera, 10 raised to power 15 peta, 10 raised to power 18 exa. Then there are for certain smaller values, 10 raised to power minus 1 deci, 10 raised to power minus 2 centi, 10 raised to power minus 3 milli, 10 raised to power minus 6 micro, 10 raised to power minus 9 nano, 10 raised to power minus 12 pico, 10 raised to power 15 femto, 10 raised to power minus 18 atto. Their symbols also mentioned in the table. You should know all these prefixes. Then in physics we have range of lengths. What all distances can we measure in physics? So distance of the farthest orbit quasar is 10 raised to power 16 meter. Distance of a galaxy 10 raised to power 20 meter. Distance of nearest star from Earth 10 raised to power 17. Mean distance of Sun from Earth 10 raised to power 11. Mean distance of Moon from Earth 10 raised to power 9 meter. Radius of Earth 10 raised to power 7 meter. Radius of Moon 10 raised to power 6 meter. Height of Mount Everest 10 raised to power 4 meter. Average height of a man 10 raised to power 0. Thickness of paper 10 raised to power minus 4 meter. Size of red RBCs or sharp pen 10 raised to power minus 5 meter. Mean free path of air molecule 10 raised to power minus 6 meter. Radius of hydrogen atom 10 raised to power minus 10 meter. Radius of atomic nucleus or effective radius of proton 10 raised to minus 15 meter. So these are the distances that can be measured in physics. So all these distances can be measured in physics. Now you will see a video in which the shortest distance and the maximum distance measured in physics is shown. So watch the video and see the maximum and the shortest distances measured in physics.